Hello, I'm Laura Marshall.
And I'm Melinda Rose, and this is Light Matters for April 24th, 2013.
On today's show, bad guys can run, but they can't hide from thermal imaging. On-chip optics makes advances. A solar dish pulls in the power of 2,000 suns, and a new system lets you read on the run.
The photonic technology of infrared imaging was literally in the spotlight this week as law enforcement officials used it to monitor and then capture suspected Boston Marathon bomber Dzhokhar Tsarnaev. On April 15th, 2 bombs exploded in quick succession more than 4 hours into the marathon. 3 people were killed and more than 140 were wounded. On April 18th, Tsarnaev's older brother, Tamerlan, also a suspect, was killed. A day later, a massive manhunt for Dzhokhar shut down the city of Boston for the day. A forward-looking infrared camera on a Massachusetts State Police helicopter helped find traces of the suspect's heat signature as he lay in a tarp-covered boat. You're watching some of that video now. Optical imaging methods for threat detection continue to be improved, and some of those advancements will be on display next week at SPIE's Defense, Security, and Sensing Conference in Baltimore.
And the April issue of Photonics Spectrum magazine is largely devoted to defense and security issues. Contributing editor Hank Hogan writes on sensor research and development to make night vision systems less expensive, bulky, heavy, and power-hungry.
And science writer Valerie Coffey shares some advances in standoff detection related to ultraviolet laser-induced fluorescence, Raman and quantum cascade laser-based detection, and trace chemical sensing.
Yeah, it's really kind of a timely topic right now.
Absolutely.
A Harvard-led team has created a new type of nanoscale device that converts an optical signal into waves that travel along a metal surface, or plasmon waves. Significantly, the device can recognize specific kinds of polarized light and accordingly send the signal in one direction or another. The findings offer a new way to precisely manipulate light at the sub-wavelength scale without damaging a signal that could carry data. This could enable a new generation of on-chip optical interconnects that can efficiently funnel information from optical to electronic devices. A surface plasmon polariton wave is a surface wave in a sea of electrons that exists inside metals. In the past, it was possible to control these waves by changing the angle at which light strikes the surface of the coupler, but it was considered a major pain. Optical circuits are very difficult to align, so readjusting the angles for the sake of routing the signal was impractical. With the new coupler, the light simply needs to come in perpendicularly and the device does the rest. It reads the polarization of the incoming light wave, which might be linear, left-hand circular, or right-hand circular, and routes it accordingly. The device can even split apart a light beam and send parts of it in different directions, allowing for information transmission on multiple channels. Because the new structure is so small, each repeating unit of the pattern is smaller than the wavelength of the visible light, the researchers believe it should be easy to incorporate the design into novel technologies such as flat optics. The work, which included co-authors from Singapore and China, was published in Science.
A photovoltaic system capable of harnessing the power of 2,000 suns and converting 80% of incoming light into useful energy could provide sunny, remote locations with electricity, fresh water, and cooler air. Current solar technologies are expensive and slow to produce, also require rare earth minerals, and lack the efficiency to make massive installations in remote locations practical. Now a collaboration including IBM Research in Zurich, ETH Zurich, and others are developing a lower-cost solution with funding from the Swiss Commission for Technology and Innovation. The prototype system uses a large parabolic dish made from a multitude of mirror facets that is attached to a tracking system that determines the best angle based on the position of the sun. Once aligned, the sun's rays reflect off the mirror onto several microchannel liquid-cooled receivers with triple-junction photovoltaic chips. The entire receiver combines hundreds of chips and provides 25 kilowatts of electrical power. Current concentration photovoltaic systems collect electrical energy and dissipate thermal energy into the atmosphere. The new system aims to eliminate the overheating problems of solar chips while also repurposing the energy from thermal water desalination and adsorption cooling. A prototype is now being tested at IBM Research Zurich.
Ever get bored on a treadmill and wish that you could read while you run? Well, now you can, thanks to a new system that studies text on a display so you can peruse as you sweat. The system, developed at Purdue University, is called Reading Mate. It counteracts the bobbing motion of a runner's head by adjusting text on a monitor so that it appears still. Reading and running is difficult because the relative location of your eyes to the text is vigorously changing, and your eyes try to constantly adjust to such changes. Reading Mate was created on the hypothesis that the primary impediment to reading while running is the head's vertical movement. The new system enables a jogger, using goggles equipped with infrared LEDs, to read normal-sized text on a small monitor mounted in front of the treadmill. An infrared camera captures the LEDs, tracking the runner's bobbing head. The text is moved in unison with the head movement as the human reflex to compensate for motion is taken into consideration. The system was tested by 15 students who carried out a letter counting task while running on a treadmill. The test required participants to count how many times the letter F occurred in 2 lines of text situated among 10 lines displayed on a computer monitor. Participants who used Reading Mate demonstrated a higher accuracy compared with those in the control group. Findings appeared in Human Factors, the Journal of the Human Factors and Ergonomics Society.
That's it for this edition of Light Matters, Photonics Media's weekly newscast.
As always, you can write to us with your comments or questions at lightmatters@photonics.com.
Thanks for watching, and we'll see you next week.
We are basically using light to make neural circuitry by guiding light in a defined path, and then stimulating the light, stimulating the neurons also using the light, and then making the circuit to see how the neural circuitry work at the in vitro level, and then also using it in vivo to understand how the whole process works.
To understand how the brain works?
Yeah, how the brain works, how in different diseases the circuitry get changed, and how neurons communicate with each other. So making the circuit, and then even we can cut particular circuit and then actually detect the circuit, how it works at the whole integrated level. The importance of it, for example, for neuronal guidance, if you have a spinal cord injury, to guide it, people have been trying chemical methods, electrical methods, and all other methods, but the people have been trying it, but there is limited success. Light being very non-invasive, we have recently shown that we can guide the neurons with light, so we are applying now to in the in vivo level, so that we can guide the neuron and bypass if there is a damage injury site and take it to the sensory site or motor site in the peripheral nervous system.
Okay.